All right, we're rolling. And of course they come in. Can you shut the door behind you? Thank you, Manus. Don't lock it, but just shut it. All right, boys. This page. We're on to conservation of momentum. Now, there's a really nice equation that you have to be familiar with. You're going to be using it. And I'm going to show you the derivation of this equation. It's not too tricky. It's a fundamental law. It says that the momentum of a system must be conserved in all interactions. That means that your momentum before the collision must be equal to the momentum after. Our system is going to be very simple. It's just two objects. All right, we're going to ignore any external forces. There's no air resistance. There's no friction. It's just object number one, object number two. Okay, so could we just add some information to this diagram? We'll say M1 is the mass on the left. And let's say that he is travelling with some initial speed u1. Let's say that M2 is stationary. Okay, so we've got the initial, and then they're going to collide. All right, so afterwards, let's just assume that M1 is now stationary, and then V2 is going to travel off, M2 is going to travel off with some velocity. Okay. So we've got a couple of equations that I'd like you to write down here. The sum of initial is going to equal the sum of the final. Now there's a few ways that we can write this. We're going to write that the sum of the initial is sigma p initial, and that's going to be equal to P1 initial plus P2 initial. So the initial momentum of object 1, add it to the initial momentum of object 2. All right? Now that is going to equal the sum of the final momenta. And so now we've got the final momentum of number 1 plus the final momentum of number 2. From this, we could say, well, instead of writing P, I'm going to write MV, but I'm going to use all of the correct notation. So P1 initial is going to be M1 initial speed plus M2 initial speed. That is going to equal M1 final speed plus M2 final speed. Now we haven't really proven anything here, but we've got a really nice equation, and this is always conserved. All right, so it's a fundamental law that the momentum before equals the momentum after. I want to show you an actual a proof during the collision. So let's just say while these cars are colliding, all right, so we've got the diagram above shows before and after. During the collision, we're going to have an action force. So that would be cart number 1 acts upon cart number 2. Newton's third law says that there will be an equal and opposite reaction force. So cart number 2 then applies an equal and opposite reaction force. So let's just state Newton's third law. F action equals negative F reaction. That's the third law. Let's introduce the second law. Instead of writing F action, I'm going to say that's going to be, well, that acts on M2. So I'm going to write M2A2 equals negative, well, the reaction force acts on M1, so that's M1A1. All right. Then I'm going to add an equation that we already know about A. That's just V subtract U over T. So I'll now go, that's M2 outside of V2 take U2 over T2. That will equal negative M1 outside of V1 take U1 over T1. It looks like it's getting nastier, but what we can say is that the two time intervals must be equal. Cart 1 is touching cart 2 in the same time interval that cart 2 is touching cart 1. It's the same time. And so we can cancel out our times. T1 equals T2. Cancel-y. Then we have well, let's just simplify it a little bit further. V2 take V1. V take U, that should have been a U there, U2. There we go, that's a little bit better. Now let's expand them out. So we'll get M2 V2 take M2 U2 equals negative M1 V1 double negative plus M1 U1. Let's put all of the initials on the left. Well, we'll get a negative equaling a negative. Let's put all the initials on the right-hand side and all of the finals on the left. For some strange reason, we'll say M1 V1 plus M2 V2 equals M1 U1 plus M2 U2. So that is our derivation of our conservation of momentum. Just in the wrong way. This is saying that the sum of the final momenta equals the sum of the initial momenta. In your data sheets, you have that equation. You have the M1 U1. Sorry, my apologies. No, you don't. You don't have this equation. I would like you to memorize it. All right? So M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. The sums of the initial must equal the sums of the final. All right? Pro 3. So let's just do a very simple example. All right? Over the page, we have pretty much a similar scenario. We have mass number 1 traveling with a speed of 4 colliding with mass number 2. All right, so all the information is provided on the left-hand side. The end goal is if mass number 2 was initially stationary, and mass number 1 after the collision is stationary, we want to know what speed did the other cart travel off with. Now, logically, if it's equal masses, then it should be exactly the same speed because all of the momentum was initially in mass number 1, then all of the momentum is then final in mass number 2. So let's use our equation. You'll need to write out the following. The sum of P initial equals the sum of P final. We then put our equation in, M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. This is one of the easiest... Yes, Matthew?
Can we not just go straight to the second?
No, I'd like you to write out all of your logic, all right?
Oh, you have to do some before. Okay.
This is the easiest scenario because mass number 2 did not have any initial and then mass number 1 did not have any final. We can either throw the values in or we can rearrange. It's entirely up to you. I'll put the values in first. So we'll go 2 by plus 4 equals 2 V2. So I'm just going to write this out in one extra step. And that is that the total initial momentum is 8 kilogram meters per second in the positive direction. Okay? Now, I've already provided a plus, so we do have a sign convention here that to the right is positive, to the left is negative. What this is saying is that in the final momentum must also be 8 kilogram meters per second. If it's belonging to an object that has a mass of 2 kilograms, then there's only a velocity that would agree that a 2 kilogram mass has 8 kilogram meters per second. So finally, V2 equals 8 divided by 2 equals plus 4. That's going to be the easiest question that you would ever solve for. Okay? I have got a simulation loaded up, knowing well that Logger Pro was not going to work. The link of this applet is on the OneNote. You can vary all of the initial conditions. You can look at the velocities, you can look at momentum, things like that. So in this example, we've got a cart coming in at point 2. We've given equal masses. So this is what I wanted you to see using Logopro 3. Boing, and away it goes. Okay? And you can see the velocities afterwards. You can choose momentum instead. Before we had 0.1 kilogram meters per second, after we had 0.1 kilogram meters per second. Okay? Now let's make things a little bit trickier. Let's have more than 2 speeds. Let's have, not being stationary before and after. So let's go back to our booklet. Let's look at scenario 2.
So
A 3 kilogram mass. Let's write everything down. M1 equals 3. I'm going to assign right as positive. All right, have a look at the board. We've got an important word here that it's recoiling. So if you have a light mass colliding with a heavy mass, it's actually going to recoil. Maybe I should be able to replicate this by placing my stapler on mass number 2, making it a little bit heavier. All right, thinking on my feet here because I don't have the Pasco weights. Guys, have a look at the front for me for a moment. I'm going to replicate this with a light mass colliding with a stationary heavy mass. Are you ready? Ooh, they travel backwards. All right, Cameron wasn't watching. We're never going to repeat that experiment ever again. Here we go. All right, they recoil. So momentum is conserved though. So if we have one piece of information about the final conditions, which is recoiling at that speed, we can figure out the speed of mass 2. So let's write it in. So afterwards we have V1 is negative 1.6, and this is the important thing. Okay? So you have to include your sign convention. If you forget that negative, you're not going to get the right answer. Okay? So please write all of your logic in. Sum of momentum initial equals sum of momentum final. M1U1 plus M2U2 equals M1V1 plus M2V2. The more you write that equation down, it's going to roll off the tongue as you are writing it down. Conveniently, the total momentum at the start is solely from M1, so that's going to be 3 by plus 2. That means we have a total momentum of 6 kilogram meters per second right. And so afterwards, the total momentum of cart 1 plus cart 2 must also be 6. All right? This is just a fundamental conservation law of nature. Let's throw in our values. M1 recoils now, so that's going to be 3 by negative 1.6 plus 6V2. Okay. So again, it doesn't matter whether you rearrange at the start or you put the values in and evaluate. So we'll go 6 equals negative 4.8 plus 6V2. We'll solve it in one step. Divide it by 6. 10.8 divided by 6. Calculator spits out plus 1.8. Okay.
So,
Yes, Cameron.
well, what if you don't know how fast either of the mass is going to be on the other side? How would you work that out? Because it's going to be the same thing every time.
There is a way to solve it, but we need to look at energy considerations. So, gentlemen, there can be a method of solving for both velocities without given one, but it's quite tricky. We need to look at energy considerations. We can get an expression of the velocities from energy and then substitute it into the momentum expression, but we'll do that after we've learnt about energy. There's no point doing it now. We can come back to this scenario and go, if it was perfectly elastic, then yes, we can solve, but it becomes a lot trickier. All right. So better off, I give you a recoiling velocity, you can solve for one unknown. All right. Have a go with this one.
So this question, should we just use this done?
No. Ignore it. Do the question that's on the screen.
I have done questions.
All right, then just sit there quietly.
Do we need to
Have a go of this question, please. You'd need to assign a convention, as always. For now, and in fact for most questions in tests and exams, I would still like you to write your values down on the left-hand side. M1. Okay. So just before you start approaching and attacking this question, have a look at the screen again. I teach this every year, and every year some students will forget the negative. Okay? Also, when you rearrange this equation, you're going to have to subtract one term from another. You're going to get a double negative. So be careful, that negative is attached. It is a vector direction. So don't confuse your vector directions with your addition and subtraction mathematics. Okay? Throw all the values in. M1 V1 plus M2 V2. Let's throw our values in. 5 by plus 4. 3 by negative 3. Yes, since you asked so nicely, we will. I'm going to evaluate the initial momenta. So that's plus 20 minus 9, we get plus 11. Okay? So even though we've got two objects traveling in opposite directions, one of them has more momentum. All right? And it turns out that the object traveling to the right has more momentum because when you sum the momentum, we still have plus 11. All right? So now at the end, this side has to also equal plus 11. So we'll throw in a plus 5 plus 3 V2. Solve as normal. So we'll go subtract 5 from both sides. Plus 6 equals 3 V2. V2 equals plus 2. Or 2 meters per second right. Now, could I replicate this? I'm not sure. I'd need to get the masses correct. I'd need to make sure that this mass was about 60% of the other mass, and I'm not sure if I'm able to, but let's give it a go. Are we ready?
Yeah. A very heavy one, as long as and you allow one going at the same speed, it should work.
No, I'd have to have the ratio of the masses correct and the ratios of the velocities correct. I'm not really able to do that with a stapler at the moment. Here we go.
You could stack parts.
Ooh, he almost travelled in that same direction. So if we put a little bit more mass on this guy, we might be able to... Ooh,
A little bit more pace though. The blue one less pace.
I'm not going to worry, but we had a go. Let's see if I can go to our animation. Am I able to change things? Well, let's just make one of these masses that's not the keyboard I require. Thank you. Let's just make one of these masses a little bit lighter. I give up.
Just type so. Just try and type.
You can't.
Let's not look at that applet. Let's go on to the next scenario. Okay. Now, in this question that we just did, the two t terms cancelled. When we derived this equation, we didn't have to worry about force. We didn't have to worry about acceleration. We didn't have to worry about a time interval. They were common, and so we just had m's and v's, and we could play around with the m's and the v's. But let's just say that we've now determined that they were in contact for a certain amount of time. So we want to determine the force acting on mass number 1. Let's write our information down about mass 1. We said it was a 5 kilo mass, and it was initially travelling at +4, and then it was afterwards travelling +1, and we now have our time interval of 20 milliseconds. The question is, what is the force? All right. Now, let's take that massive long equation that was in the pink or purple box from a couple of lessons ago. Let's write it all down. Impulse equals F delta t, which equals change in momentum, which is P final minus P initial, which is M1 V1 minus M1 U1. This is just for cart 1. All right, so we're just putting all of the information down for cart 1. The change in momentum of cart 1, the force acting on cart 1. I could put little subscripts everywhere. I could put impulse of cart 1, force of cart 1, time interval, change in momentum, 1, 1, 1. We don't care about cart number 2 for now. Okay? Well, what do we have on the left-hand side? We've got the M's and the V's, and we want to figure out what is the force. So let's just take that and select that for our equation. F1 delta T1 equals M1 V1 minus M1 U1. Rearrange for F.
20 milliseconds.
0.020. We are now back to Newton's second law. Remember, we started with F equals ma, and we picked it apart and we said, well, what Newton actually said, that a force acting in a time period would cause an object's momentum to change. So we're back to what we learned in the first lesson for momentum. Let's throw everything in. 5 by +1 minus 5 by +4. That's right. So 7.50 by 10 to the 2 newtons left. That should make sense. If the car was travelling right and collided with an object, then the impulse must be left. The force acting to produce that impulse must be directed left. The change in momentum, this number here, that's the change in momentum. Have a look. That's mv minus mu. That's delta p. So we know that the change in momentum of the cart was 15 kilogram meters per second left. Right. Quick question. We're not going to write it down because we don't have enough room. If I put all of the information down for mass number 2, what would the answer be? 750 newtons right. If you have the answer, put your hand up. Yes, Cameron.
750 newtons right.
Absolutely correct. Which one of Newton's laws would explain why we get an equal and opposite force? Yes, Cameron. No, Sam.
The one that is about each force will have an equal and opposite reaction.
1, 2, or 3?
The third.
The third.
The third, yeah.
Newton's third law. So
No idea.
we could have done exactly the same thing. Newton's third law says that this number here would be equal and opposite. So if time is the same, which it was, then this numerator would have to also be equal and opposite. So the change in momentum of mass 2 would be 15 kilogram meters per second right. The force acting on mass 2 would be 750 newtons right. Okay? Alrighty. We're doing pretty well here. Let's get on to the next kind of collision. And this is called a coupling. I'd like to demonstrate this. Yes, Brady?
We want to block. Can we not F equals ma and then use your values?
You could have, yes, but you would still need to determine acceleration.
Yeah, that's by doing beta.
You could have, yes, absolutely. So if this was in a test or an exam, you could go down that pathway. There's two possible solutions. You've got to be careful though, if the question says solve using concepts of momentum and impulse, you would have to use this equation. Or if it says just solve for the force, then you've got options. Okay? Now, I've turned the cart around and now instead of repulsive magnets, we now have Velcro. Okay? So now, have a watch. My cart is going to come in and it's going to couple and then travel off. All right? I'll do it again. Doesn't matter which one's moving relative to the other. Here we go. In comes a cart and they couple. Now, it would make sense that they travel off slower because you had the same momentum before and after, but your initial momentum was acting on a light mass made of fast velocity. Then it was acting the same momentum acting on something heavier. If m goes up, v must go down, all right, to conserve momentum. So, in a coupling scenario, we're going to write all of the following information down. So, in comes cart number 1. And I'm going to place in the applet that I'm about to show you, it changes from a little spring to a little like coupling lock, like two train carriages that might connect together. Okay, so when they connect together, they don't rebound, they combine. Let's just say that cart number 2 was stationary at the start. And then over here, we're going to write M1 plus M2. They're combined together. And we're going to write that if they're combined together, then V1 equals V2. We're going to make this new term VC. Okay?
Collective.
Combined, collective, coupled. So MC is going to be M1 plus M2, and VC is going to be, V1 or V2. The equation becomes slightly different, but we're still going to show our logic at the start that the initial momentum must equal the final momentum. We'll write it all out. M1U1 plus M2U2. I'm now going to write the combined momentum is MCVC. So again, this equation is not in the data sheet. So just get familiar with writing these two equations down from today's lesson. So, consider it. M1 equals 0.1 kilograms. Initially travelling, plus 4. We had a stationary cart, so M2 equals 0.3. U2 equals 0. After the collision, we've got VC equals question mark, MC equals 0.4. All right, so once they combine, you add the masses together. Yes, Emil?
In the test, we have to show 0.1 plus 0.3.
I imagine, it would be best to show all of your working, absolutely. Don't risk it, don't risk it. Throw the equation in. Well, we've already written it above, so I'm just going to skip to M1U1 plus M2U2 equals MCVC. Let's just solve this intermediately. We had 0.1 by plus 4. So it turns out that the initial momenta was 0.4 kilogram meters per second. Okay. Alrighty. Let's have a go at the following question. In fact, you've got all of the questions on the next page. This one's going to be a bit trickier, gentlemen, because we now have two carts travelling in opposite directions. All right, so please remember, assign your convention. Well, positives and negatives. I know it's not asking you for a question here, but the end game is find VC.
And whichever has more momentum is getting.
Yeah, so this is now whichever mass has the most momentum, sort of, what would you say? It dominates.
It keeps going.
Well, when they couple, it'll travel in the direction of the object that had the most momentum. Okay?
Do we need to put in a sign convention if they